our previous lectures we have discussed about second law and entropy, and it is I think a very appropriate time that we start solving some problems on entropy, of course by first considering a control mass system. So, we will start with the problems in entropy. The first problem that is going to be displayed in the slide. So, you can refer to this problem 6.1. So, 1 kilogram of ammonia in a piston cylinder at 50 degree centigrade 1000 kilopascal is expanded in a reversible isothermal process to 100 kilopascal. Find the work done and the heat transfer during the process. So, this problem appears to be very simple, but I will show you where the novice students fall in trap in solving this kind of problem. So, let me go to the board and try to solve this. So, there is a piston cylinder arrangement. So, the system is ammonia, mass is 1 kg, this is at 50 degree centigrade and 1000 kilopascal. So, state 1, T1 is equal to 50 degree centigrade, P1 is equal to 1000 kilopascal. It is expanded in a reversible isothermal process. So, T2 is equal to T1 is equal to 50 degree centigrade and P2 is 100 kilopascal. Find the work done and the heat transfer. So, I will solve the problem in the intuitive way, the way in which it should be done, and then I will tell you that where do students make mistake in solving this problem. So, what is given about the process from 1 to 2, that is it is reversible plus isothermal. When it is reversible, you can use del q equal to TdS. Okay. So, the total heat transfer from 1 to 2 is integral of TdS, and here temperature remains constant during. Okay. So, this is T into S2 minus S1. So, this is T into M into S2 minus S1. So, how do you know S2 and S1? From ammonia table. So, the substance is ammonia. So, so you will know S1, you will require other things also from ammonia table. And this will give you what is S2. M is 1 kg and T is, so when you write it is here it is 273.15 plus 50. Any expression that has evolved from the second law, the temperature has to be put in the absolute scale, because the absolute scale has its basis or genesis in the second law itself. So, then if you substitute these values, you will get the heat transfer. So, I am giving you the answer. The heat transfer is 396.967 kilojoule. How do you get the work done? Now you apply the first law. So, this heat transfer you already know, internal energy from table. So, not just S1, you also require U1. So, these are from table. So, this will give you what is W12. So, W12 is equal to 363.75 kilojoule. Okay. Now, I have some experience of teaching thermodynamics over the years, and I have tested several times by giving the students this problem to solve, and once this problem is given to the students, their eyes light up, because this appears to be such an easy problem, everybody wants to solve it immediately, and the answer that the students write is P1 V1 ln V2 by V1 is the work. Why? Like the keyword isothermal. For an isothermal process, from school they have learned this formula, that integral PdV. For an isothermal process, this will give you P1 V1 ln V2 by V1. So, they will do that, and this is completely wrong here. The reason is that formula that is learned from school level for an isothermal process is for an ideal gas, and here this is, nobody has told that this is an ideal gas. So, first you calculate the heat transfer, then you calculate the work done, and you can clearly check that this is not equal to P1 V1 ln V2 by V1. You have clear data of V2 V1 P1 V1 from the table, and you can check that that is not happening. So, these are very simple traps where students can fall, and you have to be very careful and judicious before using a formula, that whether that formula is appropriate for that kind of a situation.
Sir, we could as well use integral PdV here, right?
You could use integral PdV, but integral PdV is not a problem, but how do you know the path? PV is not equal to constant. This is an isothermal process, but all isothermal processes will not have PV equal to constant. So, integral PdV you use, but integral PdV in this case will not boil down to P1 V1 ln V2 by V1, because PV is not constant. Okay. So, I will erase the board before solving the next problem. So, problem number 6.2. Water in a piston cylinder shown in the figure, which is below the statement, is at 1 megapascal 500 degree centigrade. There are two stops, a lower one with V minimum as 1 meter cube and upper one with V maximum 3 meter cube. The piston is loaded with a mass and outside atmosphere such that it floats when the pressure is 500 kilopascal. So, all these full statement is given just to make sure that when the piston moves in a quasi equilibrium process, the pressure that is resisting is same as 500 kilopascal. The setup is now cooled to 100 degree centigrade by rejecting heat to the surroundings at 20 degree centigrade. Find the total entropy generated in the process. Okay. So, to work out this problem, we will go to the board and draw the schematic. there is water, okay. This is the gravity direction. So, the system is water, state 1, one MPa 500 degrees centigrade. Okay. So, then what is physically happening? Let us try to understand it. When heat is transferred from this to a thermal reservoir located maybe here at temperature T0, there is a heat transfer. So, when this heat transfer is taking place, when heat is being lost, what will happen? This piston will start coming down, right, because it loses energy. So, it will come down. So, in the process, the question is that will it hit these stops, because if it hits these stops, then its volume cannot change further. So, let us check that. So, it says that the setup cools to 100 degree centigrade. So, let us try to draw a PV diagram. It starts with state 1. At state 1 the pressure is 1 megapascal, but it starts moving. When does it start moving? It starts moving when the equilibrium pressure is 500 kilopascal. So, till the pressure becomes 500 kilopascal, this will not start moving. So, as heat is rejected from this, the pressure inside will drop, and when the pressure drops from 1 MPa to 500 kPa, till that time the volume remains constant, the piston does not move. So, this is your Vmax. In this Vmax state, it remains like this. Then when the pressure has become 500 kilopascal, that is P equilibrium, then it starts moving. When it starts moving, it will move with this equilibrium pressure, because the resistance pressure does not change, the internal pressure also will not change during the quasi equilibrium process. Question is, does it hit the stop? Because if it hits the stops, then its volume cannot change further. So, when it reaches the stops, what is its volume? Lower. So, that volume is given. The volume given here is what? 1 meter cube. By the way, how do you know what is the mass of water in the in this cylinder? So, state 1 also has V1. So, V1 is Vmax, which is 3 meter cube. So, you can find out the specific volume of this from table. So, the mass which does not change during this process is volume by V1 by specific volume at state 1. So, V stops you know. So, what is specific volume at stops lower is equal to V stops by M. What is the pressure? Just as it you know, just when reached. is equal to 500 kilopascal. With this combination you see what is the temperature, is it greater than 100 degree centigrade or less than 100 degree centigrade, because your final temperature is 100 degree centigrade. So, check with this what is T, it will come out to be greater than 100 degree centigrade for this problem if you work out. So, see, that is why thermodynamics is such an interesting subject. Had it come to 100 or less than 100 degree centigrade, the process would stop maybe even before this, less than 100 degree centigrade, I mean if this is less than 100 degree centigrade. So, whether the process will continue up to this lower stop and continue further, that depends on what numerical value you are getting from this answer. So, there is no formula by which you can solve this problem. You have to assess the numerical value and based on that take a decision. Here the temperature is 100 degrees, greater than 100 degrees centigrade when it reaches the V minimum. So, this is your V minimum. So, when it reaches V minimum, its temperature is greater than 100 degree centigrade. As per given data of the problem, state 2 will be the temperature condition at which it becomes 100 degree centigrade. So, heat is now, because it has already reached the lower stops, it will reject heat now at constant volume till the pressure comes down and also temperature comes down. So, the state 2 is somewhere here. So, how do you identify state 2? State 2 is, you have V2 is equal to V stops lower by m and T2 is 100 degree centigrade. These two property values will identify state 2. Okay. So, identifying the state point is all about solving the problem, then it is a matter of using the first law and second law. So, first law, so the structure of these problems is, to calculate entropy generation you require what? Heat transfer. To calculate heat transfer you require first law. So, to solve these problems you require combination of first law and second law. So, first law Q12 okay. So, U2 and U1 you get from table. And work done, what is that? So, let us say this is 1 prime, this is 2 prime. Work done is integral P dV between 1 prime to 2 prime. So, this is nothing but P equilibrium into V2 prime minus V1 prime. So, this is V minimum, this is V maximum. So, we will get the heat transfer. Let me see if I have the value. Yes, heat transfer is minus 2677.5 kilojoule. As I have told you earlier that it is absolutely important to make sure that you have got its sign physically consistent. Here heat is rejected. So, heat transfer should come out to be negative. If it does not come out to be negative, you must get the first alarm that your solution is not correct, and then please revisit the calculations. These are common sense checks that you can make to make sure that the solution that you are doing is consistent physically. And then we will apply the second law. So, m into S2 minus S1 is equal to Q12 by T plus S gen, right. Now, the big question is, See, everything we know, S2, S1, these are from table. Heat transfer also we have calculated from first law. The big question, and I will discuss a little bit about that, is what is this T? Well, this is a very important question. It depends on what you want to find out. You want to find out entropy generation only due to internal irreversibility. If you want to find out entropy generation only due to internal irreversibility, that T is the temperature at the system boundary. If you want to find out net entropy generation in the system and surrounding together as a universe, then your system boundary shifts from here to here, because then that includes this heat transfer also. So, here what is asked is find the total entropy generated in the process. Total entropy generated in the process means not just due to internal irreversibility, that entropy generated due to internal irreversibility plus entropy generated due to the external heat transfer, and that is why you have to substitute here T equal to T0, and that also in Kelvin. So, what temperature you substitute here depends on entropy generation for what you are calculating. Okay. So, this is 273.15 plus 20 Kelvin, and then the final answer to this is 26.27 kilojoule per Kelvin. Okay. So, we will continue with the problem solving. Let me erase the board for this problem. So, problem 6.3. There is a vertical cylinder piston of volume 50 liter. It contains R22. R22 is a refrigerant. R for refrigerant at minus 20 degree centigrade, 70% quality. The cylinder is brought into a 20 degree centigrade room and an electric current of 10 ampere is passed through the resistor inside the cylinder. The voltage drop across the resistor is 12 volt. It is claimed that after 30 minutes the temperature inside the cylinder is 40 degree centigrade. Is it possible? So, to assess whether it is possible or not, we have to check whether it satisfies the second law. That means entropy generation, whether it is positive or not. If entropy generation somehow comes out to be negative, then that means such a process cannot be feasible. So, let me go to the board, draw the schematic and solve this problem. So, the fluid is R22, state 1, T1 is minus 20 degree centigrade, X1 is 0.7, V1 is 50 liter, that is 50 into 10 to the power minus 3 meter cube. State 2, see this piston, it moves, it floats freely, right. So, it is moving in a quasi equilibrium process without any change in the external resistance. So, P2 is equal to P1 is equal to P equilibrium. So, P1 you can, P1 is what? Because this is in the two phase region, P1 is saturation pressure at minus 20 degree centigrade. This is P2 and T2 is 40 degree centigrade. This is the claim. So, let us find out the entropy generation, again it is a two step process. First we will calculate the heat transfer using the first law, and using that heat transfer we will calculate the entropy generation. See, this is a very important understanding. Entropy generation is not associated with work done, but it is associated with heat transfer, and entropy generation essentially talks about lost opportunity of doing work. So, work is considered to be a high grade energy, high grade form of energy, where there is no dissipation due to entropy generation, but heat transfer always will have a lost opportunity of work associated with that, and that therefore leads to entropy generation. So, then let us apply the first law. How do you calculate the mass? So, you calculate the mass by noting that you have total volume V1. So, from state 1 property table you know what is specific volume. So, mass is this one, U2 and U1 also from table. The key to this problem solving is the expression for work done. So, here you also have an electrical work because of the flow of current against a voltage. So, it is also like a displacement against a resistance. So, here this will be integral PdV plus W electrical. What is this W electrical? The electrical work is minus voltage into current into time. Why minus? Because you are inputting some energy to the system by creating a current across this voltage. So, if energy is supplied in the form of work to the system, it is negative work. If energy comes out of the system due to work, that is positive work. So, that is why negative. Volt into current is the power into time is the total energy, right. So, voltage etc., voltage, current, all those things are given. 12 volt, 10 ampere and 30 minute should be converted into second. So, integral PdV is P equilibrium into V2 minus V1. V2 is mass into specific volume at state 2, specific volume at state 2 from table. So, then you can calculate what is heat transfer. I do not have the value of the the expression, but you can always calculate it numerically. Then the only step is second law. So, m into S2 minus S1 I am straight away writing T0, because if you want to calculate the total entropy generation due to heat transfer plus internal process, then T has to be T0, and here also T0 just like the previous problem, it is 20 degree centigrade, that is 273.15 plus 20 Kelvin. So, all these can be substituted. This is from table, this is from table. So, from here you can find out what is entropy generation, and the entropy generation is 0.768 kilojoule per Kelvin. This is lowercase k for kilo, this is uppercase k for Kelvin. These things you have to be little bit particular. So, because entropy generation for the net process is greater than 0, this is definitely feasible. At least the claim cannot be ruled out that after 30 minutes the temperature inside the cylinder is 40 degrees centigrade. That heating is a feasible heating. So, we have solved 3 problems on entropy today. We will continue with more problem solving in the next lecture. Thank you very much.